sure I remember how to do them.
Yeah.
So, what should we do first? Let's look at what is this, problem 4?
Yeah.
Okay. So they want the volume of the solid whose base is between secant x and the x-axis from pi over 4 to pi over 3. And its cross sections taken perpendicular to the x-axis are squares. So what do we need to do first? Just to give us an idea of what the hell they're talking about.
I think we should probably draw the graph first.
Correct. Okay. What do we know about secant? It sits on the tops and bottoms of the cosine curve.
Correct.
So, here, let me turn on my writing thing. And let's see, its period is going to go out to pi, I believe. Oh my goodness, pi over 2 is way over here. Here, let me just refresh my geometry or my trig. There's the cosine curve, so the secant curve sits there, and there, and there. And this is pi. Now, hold on a second. Let's see, this is 2 pi. So that's pi. So they're talking about from pi over 4 to pi over 3.
Right.
And let's erase my cosine curve so that it doesn't get in the way of our seeing what's going on. In fact, I don't need any of these other stuff here. We're going to deal with this area right here. And they want the base. Say we're going to build a paperweight. And you want it to be this shape on the base. And then on top of that paperweight, that flat piece of paper, you're going to put squares. So there's a square, let me use a different color. So there's a square, and the squares are going to be perpendicular to the x-axis, but then the next square needs a bigger square, right?
Right.
And the next square even needs a bigger square still. And then we're going to sum up the volume of all of those squares, and that's going to be our answer. So, if I sum up the volume of all of the squares, I'm going to go from pi over 4, this point right here, to pi over 3, and the volume of a particular square is its side length squared. Well, what is that first square that I've drawn there on the left, the smallest one? What is its one dimension that you need to know?
Well, wouldn't its side length be secant x?
Exactly. So it's secant x squared dx. In other words, if you imagine each of these squares to have very, very small thinness, imagine a deck of cards that were cut in various shapes of squares, and you put them side by side, you would create this object they're talking about.
Right.
The first square would have a dimension of secant of pi over 4. The
Right.
last square is going to have a dimension of secant pi over 3. So we're going to take the y value, which is secant x. We're going to square it. We're going to multiply by the thickness of each piece of cardboard. That's dx. And this gives you the volume of each. That gives you dv. That's the volume of each square. And that's really a good way to look at it. Okay?
Right.
So is all we have to do is solve this now. That's definitely what we're looking at. What's the integral of secant squared?
Wouldn't it be tangent x?
Yeah. So the answer is going to be tangent x evaluated from pi over 4 to pi over 3. Well, everything in calculus is radians. So what is the tangent? We start with the top. So we have the tangent of pi over 3 minus the tangent of pi over 4.
Right.
Because it is a definite integral, we don't have a c. The c gets thrown out in the wash, kind of cancels itself out. So pi over 3 is 60 degrees.
So that would be.
If I draw my triangle, the two triangles you always need in these things is the 30, 60. Opposite the 30 is 1. Square root of 3, 2. So what is the tangent of 60 degrees?
Tangent.
Tangent's opposite over adjacent.
So 1/2.
No.
Or no, root 3 over 2.
No. Tangent, not sine. Tangent is opposite over adjacent. So what's opposite to 60? The opposite to 60 is root 3.
Yeah.
The adjacent, when they say adjacent, they never mean the hypotenuse, even though the hypotenuse is adjacent to that angle. When they're talking about adjacent, they mean the short side that's adjacent.
Okay, so it's root 3 over 1, so root 3.
So that's root 3. And the tangent of 45 degrees, we know, is 1. That's an easy one. It's just a 45, 45, 1, 1. So there's your answer. Root 3 minus 1 is the volume. Now, they don't put units on this, and I'm kind of glad they don't. No reason to make it more confusing.
Right.
But that's what you do. Now, if your shapes, and they don't have to be squares, they might be equilateral triangles, they might be rectangles, they can be semicircular coverings. They all are going to, you're going to be able to get their little tiny volume based on what y is.
Okay.
Okay? Now, when we go perpendicular to the y-axis, we've got to do an integral that is dy. Notice that this is dx because our skinny part is along the x-axis, right? Our skinniest part of the square that we're putting up is along the x-axis. That means we're going to do it with a dx. If my squares are going this way, then the skinny part is along the y-axis, and we're going to need to use a dy.
Okay. So then we would put the equation in terms of y.
Well, we'll go to the next problem, and I'll show you what I mean.
Okay.
Was there only one problem on that last page, or did I? Here,
no, there's 4 and 5.
Okay, we want to look at 5. Thanks for sending them in this orientation. That's perfect because when I blow it up twice, it rotates itself.
Sweet.
90 degrees to the left. So here we're going to go relative to the y-axis with squares. Hold on a second. Sometimes this thing really acts up. There we go. Okay, so we've got y equal x cubed. Well, we know what that looks like. That looks something like this. Right?
Right.
Okay. And they want to go from y equals 0 to y equal, this must be a quarter, a half, 3/4, a 1. So this time our squares are going to go this way. What's the size of each square?
X cubed?
No.
But it would...
Not y. What is it? It's x.
Right.
So we got to solve that for x. In other words, we have to get our equation in terms of x. Well, if y equals x cubed, then x equals the cube root of y.
Right.
All the time. There's no plus or minus involved, which is good. Plus or minus confuses the issue. So
right.
Now I have x as a function of y, which is what I need. Because each one of these rectangles has a dimension of x. So this time I'm going to sum the x. Well, what is x equal to? Y to the 1/3. And my skinny section of each square is along the y-axis, so I'm going to do it over dy. And I'm going to go from 0 to 1. Now, we can finish that out, but I suspect you don't need to.
No, I can do that one.
Okay. So it's all about where the skinny section of the square or equilateral triangle or semicircle, which axis is that skinny section being measured on? In this case, it's the y-axis. In the previous problem, it was on the x-axis.
Okay.
Okay. So, yeah, that's easy to integrate, and evaluating it from 0 to 1 is going to be easy. And we can see it's definitely going to be all positive. Actually, in problems like this, it doesn't matter whether it's on the other side of that x-axis or not. If they'd have said go from -1 to 1, we'd have had twice the volume.
Okay.
In other words, if they go all the way down to here with their squares, volume of those squares is still positive, regardless of whether it's below the x-axis or not.
So if you're taking the volume with squares perpendicular to the y-axis, it doesn't matter if it's
well,
positive.
I wouldn't say that. No, if you're looking at area, it is going to matter. It's going to be similar to the x-axis. But when you're looking at volume, notice that these squares come out of the page at you.
Right.
So the volume is only positive. There is I'm not sure exactly. If we were actually doing this from -1 to 1, I wouldn't do it like this. I would recognize that they're symmetrical, and whatever you get from going from 0 to 1, you can multiply by 2, and that would give you the total volume.
Okay. Because volume is just positive because it comes out from the page.
Well, volume is definitely always positive, yes.
Okay.
Unlike area, where area below the x-axis is negative when you do an integral of it.
Right.
With the volume, I'm not quite sure whether I would get exactly the same thing if I do 2 times this, or if I did it from -1 to 1. I think I'd get the same answer, but I'm not 100% sure.
Okay.
But I am 100% sure that they're totally symmetrical, so always do it the easiest way. And it's much easier to do an integral from 0 to 1 than it is from -1 to 1.
Right.
And then just multiply it by 2 if it's symmetrical.
Okay.
All right, let's have a look at number 6. Have you gotten yet to solids of rotation, where you take a function and you rotate it over the x-axis and you find the volume of that solid using disks or shells?
Yeah, we don't use the shell method. We use the disk or washer method.
Okay. The shell method is the tough one.
Yeah, our teacher said that this year it probably won't be on the AP test.
You're right. It isn't on the AP test.
Okay.
Every other AP student in BC Calc did not have to learn the shell method, and they also didn't have to learn integration by trig substitution, which is good, because that's another toughie. These
Okay.
integration methods that you've learned 3 or 4 of them right now?
Yes, sir. Yeah.
It's harder.
Okay.
I mean, every one of them. Partial fractions is a little harder than U substitution, and then you get into doing integrals of trig functions. That's a little bit harder. And then you substitute trig functions for polynomials so that you can integrate it, and then you convert it back to polynomial. Sometimes you get such a complex polynomial you can't figure out how to integrate it. But you can substitute all these trig functions for it. And it turns out that taking integrals of trig functions is easier than taking integrals of polynomials. So, and there's more methods after that, including infinite series. But integration is not like differentiation, as I'm sure you realize by now.
Right.
You can't just apply 4 rules. The product rule, the quotient rule, the chain rule, the power rule. That'll handle every kind of function and differentiating it. But when you go to integrate it, whole different story. All right. So here, again, we've got cross sections that are square that are going to be perpendicular to the y-axis. Well, let's graph this function. Now, for me, I can graph it better if I put it in terms of y.
Okay.
So let's do that. And then it's already solved for x. So this is going to be the side of the square. It's going to be x. But in terms of graphing it, just for my own comfort, I'm going to graph it just to see what we're looking at here. So we have y squared equals 1 minus x. So y is equal to what?
Y is equal to root 1 minus x.
Plus or minus?
Plus or minus.
And that plus or minus is going to factor in here. Okay. This, incidentally, is not a function because of that plus or minus. It does not pass the vertical line test.
Okay.
So this is going to look something like, let's see, I know what y equals square root of x looks like. So this is y equal negative square root of x. So it's going to go something like this. It's going to be a reflection. And then it's going to be moved 1 unit horizontally. Let's see, I guess I can write this a couple of ways. I can write it like this. And now I know how to graph that. And it's also this. It's not just the positive, it's also this. You see why I put the negative sign out in front and had to change it to -1 to be the same?
Yeah.
Because I know a negative sign inside the function means a reflection across the x-axis, the y-axis.
Okay.
I have to have that negative sign in front of everything. I can't leave this horizontal shift all by itself. However, that still is a horizontal shift of 1 unit to the right. So the way this thing really plots is kind of like this. And there's the plus side of it. the blue line, and the minus side is that. It's like a circle. If you solve the function of a circle, you get y equal plus or minus. The top half of the circle is the plus, the bottom half is the minus.
Okay.
Not a function, but in this particular case, we don't need it to be a function. Let's see. We're finding the volume whose base is the region bounded between the curve and the y-axis. So they're talking about this region right here. You with me?
Yeah.
Okay. And we're going to put our squares, I draw them in pink, like this. That first square is going to be real tiny. And then the next one is going to go there, and there, and there, and there, so forth. So we're going to integrate from the lower limits. Well, what's this point right here? We got to figure out what that is.
Okay. Would you factor the 1 minus y squared and find the zeros?
Well, let's see. If x is 0, y is minus 1. So I haven't drawn that quite right. Let me redraw it. In other words, we need to find out where those y-intercepts are. And
right.
I know the vertex of that thing is there. I'm pretty sure it goes like this. Because when x is 1, y has to be 0, which it is. And when x is 0, y is plus or minus 1. There's the plus 1, there's the minus 1.
Okay. So then we're integrating from -1 to 1.
Yeah, exactly. They didn't tell us that. So we had to figure it out by solving for those zeros.
And would this be the case where we would just double the volume?
You got it. In fact, we might do it both ways if we have time, just to see whether it's the same. I'm going to do it this way.
Okay.
And what goes inside that integral, or to the right of that integral sign?
1 minus y squared squared.
Good. dy. Very important. That dy. And now you can see that that squares rather normally. In other words, I'm going to get 1 minus 2y squared plus y cubed dy. Right?
Right.
I think that's what happens if I FOIL that out.
Right.
And now each one of those are easy to integrate and evaluate. So that's going to give you your volume right there. And now let's take a quick look at it. The first term becomes y minus 2/3 y cubed plus y to the 5th over 5, evaluated from 0 to 1. Now it's relatively easy to figure out because zeros and ones make for a nice evaluation. So when I plug in 1, I get 1 minus 2/3 plus 1/5. So that is the volume. What is that? 1/3 plus 1/5. That's 5/15 plus 3/15. 8/15 is our volume. Now let's see if we do exactly the same thing, only we do it the more traditional way, where I go from -1 to 1, and I don't multiply by 2. So everything is exactly the same until I get up here to evaluate it. And now I'm going to take my 1, which came out to be, what was it? 8/15.
Well, did we multiply the 8/15 by 2?
Oh, we forgot to do that. So it should be 16/15 is the volume.
Right.
Okay, so let's see what happens if we go from -1 to 1. Well, the top is still 8/15, right?
Right.
So the first part, when I substitute at 1, I get 8/15. And then this time I'm going to subtract. Ooh, I'm not sure this is going to come out the same. I don't think it is. I'm going to subtract everything evaluated at -1. Well, there's y. Minus 2/3 minus 1 cubed is still -1. So everything's copacetic. And plus a -1/5. This is its evaluation at -1, unless I've made a mistake. Now,
Yeah.
what I think is going to happen is everything inside the brackets is going to add up to -8/15.
Right. Maybe.
It's going to give me 8/15 minus a -8/15, which is going to give me 16/15.
Right. So we won't get the same answer.
Yeah, I'm not sure it comes out to 8/15 now that I look at it, though. This is -5/3 minus a 1/5. That's not 8/15. -5/3 minus 1/5 is going to be that's 16/15, I think. No, 5 times this, that's -25/15 minus 3/15. You do not get the same thing. You get -28/15. Well, I did it so fast that I wouldn't bet money on my arithmetic.
Okay.
But it kind of, no, I would think the fact that each of these is an odd number should be the same. Should be the same. In other words, we don't have -1 changing anything. When you cube -1, it's still -1. When you go to the 5th power, it's still -1. When you go to the 1st power, it's still -1. So if there was a y squared in there, I'd be suspicious. I got a feeling my math just must be off.
So -1.
But you can't go wrong doing the 2 times and going from 0 to 1. And that's the way that all teachers will tell you how to do it, if you're sure you're symmetrical.
Right.
And in
this case, we are.
Yeah. In fact, all of these we've been symmetrical. Well, not the secant one we weren't, but the x cubed and this one is symmetrical about the y-axis.
Right. Well, that makes sense. So I will just, if I know it's symmetrical, I'll just multiply by 2. So the arithmetic
and go from 0 to 1, and that's usually almost always what you're doing. Is you're able to go from 0 to 1 and multiply by 2 rather than go from -1 to 1. Right. I still think both of them should give you the same answer, but I'm actually not sure anymore. Because let's see, where could I have made a mistake? That's got to be -1 for sure. That's y. That's here's where I made a mistake. Y cubed is -1, but it's -2/3. So that should be a plus.
Right, so it should be plus 2/3.
This should be plus a -1/5. Okay, so that's going to be -1/3 minus a 1/5. That does give you -8/15, which gives you 16/15. It is the same. You can do it either way. You don't have to do it the way I did it. Which is nice because they're not always symmetrical. You might have a function that's not symmetrical, and you really do need to go from -1 to 1.
Right.
All right.
Okay.
John, if you have any other questions, we still have a few minutes here, but if you're good to go, I'll let you go.
I think that's all the questions I had for. Oh, so if I'm doing a problem like this with cross sections, and it's like say semicircles,
Okay.
so instead of using the equation for a square, you just use an equation for a semicircle, like pi r squared.
1/2 pi r squared.
Okay.
There's
And then you
the
just
area
plug.
of a square. There's the area of a semicircle, and r is always going to be the distance to that function.
Okay.
In other words, r is going to be right there. If I have to cover that thing with a semicircle, actually r is half of that distance.
Right.
In other words, r is really from there to there.
Right. So you divide the function by 2.
Yes. Well,
Okay.
twice. You got to be real careful with semicircles because you've already divided it by a half because it's a semicircle. And then you have to make sure that r is only half of whatever this function is. If that function is sine x, then r is sine x over 2.
Right. And then just plug that in and keep the over 2.
Exactly.
Keep the 1/2 out front.
Exactly. The way to think about all of these things is you're trying to find the volume of that little thing. And the volume is its surface area times its thickness.
Okay.
Okay. The surface area is going to come from this, and its thickness is dx. Notice the skinny part is going in this direction.
Right.
And therefore, the radius is going to be whatever y is. They're going to tell you y is sine x, so the radius is always going to be half of sine x.
Okay.
And if you have equilateral triangles, which is another one they like to do, the base of the equilateral triangle is this distance from here to here. And there's actually a formula for the area of an equilateral triangle. I think it's square root of 3 over 4 times the side squared. In other words, this is the area, square root of 3 over 4 times s squared for an equilateral triangle.
Okay.
And you need that. Yeah, that'll be very helpful in determining what the area is of each of those, whatever you want to call it, the cap on the base.
Right. And then if it's an isosceles right triangle, it's just 1/2 base times height.
Correct.
Okay. Okay. So I just use the same basic integration, but just change the.
Now be careful if it's an isosceles right triangle. That means that that's the hypotenuse.
Right.
That's the top. So it's the base of the hypotenuse, which is your function.
Right.
And then you'd have to figure out what the area of that isosceles right triangle is. Obviously, if that's 90, it's going to break into 245. So you could do it, but there's going to be a little extra math there. So that's probably the hardest thing, is an isosceles right triangle on top of these things.
Okay.
Figure out what the area of an isosceles right triangle is if you know the hypotenuse.
Okay.
Because it's not, you can't use base times height. The only thing you know is the hypotenuse.
Right.
All right.
Okay. Thank you.
All right, thank you. It's fun working on this stuff again.
Yeah.
All right. Bye-bye.
Yeah. Have a great day.
You too.